Hey, this is Kyle, and I'm going to talk about scaling as well as making an initial guess for an IVP, initial value problem. To do this, I'll be using example 117 from our textbook. So in this example, we have a tube that has a liquid mixture of methanol and acetone, and we're going to name the liquid gas interface in this tube as position Z is equal to 0. And we're going to label the top of the tube as position Z is equal to delta. So we know that we have the standard driving force equation right here, and this is the equation we want to scale. So first we want to scale the right side to always be an order of magnitude of 1, the left side to be an order of magnitude of 1. And if we know that the left side is an order of magnitude of 1, that means that the right side also will have to be an order of magnitude of 1. So to do this, we're going to introduce a new variable, and we're going to call that eta. So eta will be equal to position Z over delta. And this eta variable is now dimensionless as it's meters over meters. And it's always going to be between 0 and 1 because at Z equal to 0, eta is obviously 0, and at Z equal to delta, eta is 1. So now using the chain rule, we can put eta into the left side of the driving force equation. This is the scaled version of the left side that we want alone. Alright, so now this is our new left side of the equation using the chain rule. So we see that we have the derivative of eta with respect to Z, and since we know eta is Z over delta, this is just equivalent to 1 over delta. However, we want this delta, and we still have this derivative of mole fraction with respect to eta, which is what we want on the left side. So we're going to want to multiply delta onto both sides of the equation so we can get rid of the left side, which leaves the right side of our driving force equation scaled to an order of magnitude of 1. And it looks, the new equation looks like the summation starting at 1 to the number of components n, the mole fraction of the component we want to find the driving force of, times the molar flux of the next component, minus the mole fraction of that component, times the molar flux of component I. And that is all multiplied. That is all multiplied by delta, since we multiply delta onto both sides. And it's still over the concentration times the Stefan-Maxwell diffusivity for the two components. So now this is our new scaled version of the right side of the equation. And we have this left side of the equation will always be an order of magnitude of 1. So we're completed with our scaling, and now we can look at making an initial guess for our initial value problem. And what we want to do is we're going to want to combine these constants into a single constant. So we're going to call that f. And we want to keep this new constant. We want to keep this new constant on the denominator. So that will mean f is going to be equal to the concentration times the Stefan-Maxwell diffusivity for the two components over delta. And now since we want to make an initial guess, we just want to know what the order of magnitude of our unknowns is going to be. Our unknowns are the molar fluxes. And we can do that by using the order of magnitudes of all these known values. So concentration, C, is equal to concentration, using the ideal gas law, concentration is equal to P over RT. Since the ideal gas law states that pressure times volume is equal to moles times the ideal gas constant times temperature, and we know concentration is just moles over volume, so if you solve for moles over volume, you're left with pressure over the ideal gas constant times temperature. So plugging pressure over the ideal gas constant times temperature into this equation for concentration, we know all the order of magnitudes of everything in here, which means we'll know all the order of magnitudes of everything on the right side of our driving force equation except molar fluxes, which is what we want. So pressure is given in kilopascals, but if we take it to base units, pascals, it's going to be 10 to the 5th order of magnitude. Stefan Maxwell diffusivities, if we take those to base units, they're going to be 10 to the negative 5th. And then R times T, since the ideal gas constant is 8.314 and temperature is given to be 328, so this ideal gas constant times temperature is going to be 10 to the 3rd. And then delta is obviously an order of magnitude of 1. So now that we have all the order of magnitudes, we can plug in. So we have pressure, 10 to the 5th, over ideal gas constant times temperature, 10 to the 3rd. Stefan Maxwell diffusivity is 10 to the negative 5th. And delta is 1. So the 10 to the 5th times 10 to the negative 5th will cancel out, and we're left with the variable we introduced, which is our denominator, is an order of magnitude of 10 to the negative 3rd. So since we know the denominator of our driving force equation is an order of magnitude of 10 to the negative 3rd, and we know the numerator depends on mole fraction of both of the components and molar flux of the components. Molar fluxes are unknown, so that's what we want to make a guess at, and we know mole fraction is defined to be an order of magnitude of 1. So that means to get an order of magnitude of 1 on the left side, we have to have the same order of magnitude in the numerator and the denominator. Well, we just solved for the order of magnitude in our denominator. It's going to be 10 to the negative 3rd. So that means the order of magnitude of these molar fluxes, we can make a reasonable guess that it's going to be 10 to the negative 3rd. And that's all I have, so thank you.